All right, let's dive right into this explainer. Today, we're mastering a super practical, over-the-shoulder configuration. We're going to map a ModbusRTU energy meter directly to BACnet IP, and we'll be using the NewroCon interface to do it. Now, if you've ever dealt with integrating field devices, you already know this translation process can be an absolute headache. But don't worry, we're breaking down the exact sample configurations straight from the user manual so you can get that meter communicating flawlessly on a modern network. Let's get to it. So, before we jump into the actual software interface, it's really vital to understand the fundamental translation job our gateway is actually doing here. On one side, we've got ModbusRTU. This is your field device level, utilizing older but super reliable serial data. And on the flip side, we have BACnet IP. That's the language of the modern building network, sitting right on an IP network. Essentially, our NewroCon device is acting as the ultimate diplomat, completely eliminating the protocol barrier between these two very different worlds. Okay, here's our quick roadmap for today. First, gateway mode overview. Second, adding the Modbus device. Third, creating register groups. Fourth, defining Modbus points. And finally, BACnet points and saving. Number 1, gateway mode overview. The best part about this first step is that you literally don't even need to install any software. It's entirely browser-based. Right under converter settings, we explicitly set our converter type to gateway from the drop-down menu. Then, we just assign ModbusRTU to serial port 1. And what that does is tell the device exactly how to behave and exactly where to expect our incoming serial data. Moving to step 2, adding the Modbus device. Navigating over to the port 1 RTU settings page, we need to punch in the device parameters. We input our device name as EM01, which just stands for Energy Meter 01, and we strictly set the device ID to 1. Now listen, this device ID is absolutely crucial. It has to exactly match the physical addressing figured on the actual energy meter sitting out in the field. Once that's dialed in, just click the Add button. Now, check out the visual feedback in the device list table. When you first add EM01, the register config status shows up as a red pending. This is basically the system's way of saying, hey, I see the device, but I have no idea what data to pull yet. It's going to flip to a green done only after we've successfully built our groups. It's kind of like a fantastic built-in checklist. Step 3, creating register groups. All right, before clicking any more buttons, you always want to consult your vendor datasheet. For our specific energy meter, the first block of data requires a floating point data type, starting at address 3000, with a length of 100. And here is a golden rule to remember. Because floating point is 32-bit data and standard Modbus registers are 16-bit, that length value absolutely must be an even number. If it's not, you're literally just going to get garbage data. Applying that exact logic to the UI, we click the little green gear icon next to our device to open up the register configuration. Under Add Register Groups, we click the Data Type dropdown and just select F Floating Point. Honestly, the interface makes it incredibly simple to support different types, whether that's unsigned 16, signed 32, or, like in our case today, floating point. Right below the data type, we set our register type. For this one, it's O3, holding register. Then we input our starting address of 3000 and that even length of 100 we just talked about. This single configuration step is a real game changer because it grabs a massive block of continuous data from the meter all at once, which makes it highly efficient for network traffic. Now, energy meters often have data scattered all across different address ranges. So following the exact same procedure, we'd also quickly add a second register group just to capture frequency data. According to the sample datasheet, this one sits at a starting address of 3110, and since it's just one single piece of 32-bit floating point data, our length here is exactly 2. Section 4. Defining Modbus points. So to pull our very first metric, which is current A, we're going to use some simple offset math. Think of it kind of like finding a specific folder inside a giant filing cabinet drawer. We take our group starting address of 3000 and add an array index of 0. This gives us an effective target address of exactly 3000. The system actually uses this index to easily step through that giant block of 100 registers we just created. Looking at the points configuration, we set the point type to AI for analog input. We name the point CURRA, so it's super easy to identify later, and we enter that array index of 0. Notice how the interface helpfully calculates the final effective address of 43,000 right at the bottom. It automatically tacks on the standard Modbus holding register prefix of 4 to our address, effortlessly mapping the physical data for us. After repeating this offset process for all the specific variables listed in your datasheet, current B, current C, voltage AB, active power, and of course that frequency point from our second group, you get rewarded with this beautifully organized Modbus point details list. As you can see, every vital metric from the energy meter is now cleanly indexed and perfectly named.
And finally, Section 5, BACnet points and saving.
By hitting Save on our configuration and navigating over to the BACnet IP server settings, we're greeted with our final output. We can instantly verify that all our Modbus metrics, the currents, the voltages, the frequency, are now automatically and cleanly mapped as standard BACnet analog inputs. The whole shebang is there. They've got standard ID numbers, full descriptions, and they are completely ready for any modern building management system to instantly discover them right on the IP network. And just like that, the translation is complete. You've successfully bridged decades of technology, completely turning legacy serial data into instantly discoverable IP data for your network. So with these protocol barriers finally out of the way, what complex system will you bring into the future next? The possibilities are honestly endless. Thanks for joining me on this explainer, and keep learning.